sklearn neural network. Description: the neural network module in scikit-learn provides a set of tools for building and using feed-forward neural networks for classification and regression tasks. It offers implementations of the multi-layer perceptron (MLP) with different activation functions and optimization algorithms. Inputs: data: a 2D array representing the features of your dataset. Each row corresponds to a sample, and each column represents a feature. Labels: a 1D array containing the target values for each sample in the dataset. For classification problems, these labels are typically integers representing different classes. For regression problems, these labels are continuous values. Outputs: predictions: a 1D array containing the predicted target values for new data points. Model: a trained neural network model that can be used to make predictions on new data. Steps: data preparation: the input data needs to be pre-processed before feeding it to the neural network. This might involve scaling features, handling missing values, and encoding categorical variables. Model definition: you choose the architecture of the neural network, including the number of hidden layers, the number of neurons in each layer, and the activation function used in each layer. Model training: the neural network is trained using the provided data and labels. The training process involves adjusting the weights and biases of the network to minimize the error between the predicted and actual target values. Model evaluation: after training, the model is evaluated on a separate test set to assess its performance on unseen data. Metrics: accuracy: the proportion of correctly classified samples in a classification task. Precision: the proportion of correctly predicted positive samples among all samples predicted as positive. Recall: the proportion of correctly predicted positive samples among all actual positive samples. F1 score: the harmonic mean of precision and recall. Mean squared error MSE: the average squared difference between the predicted and actual target values in a regression task. Visualization plots: loss curve: a plot showing the training loss over time. This can help to assess the progress of the training process. Activation histograms: histograms showing the distribution of activation values in each layer of the network. This can help to understand the activation patterns within the network. Decision boundaries: visualizations of the decision boundaries learned by the network. Particularly helpful for classification tasks. Fine-tune parameters: hidden layer size: the number of neurons in each hidden layer. Activation function: the function used to introduce non-linearity in the network, such as ReLU, sigmoid, or tanh. Learning rate: the step size used during the optimization process. Number of epochs: the number of times the entire training dataset is used for training. Uncertainty methods: dropout: a regularization technique that randomly drops out units during training, leading to a more robust model with less overfitting. Monte Carlo dropout: a method for estimating uncertainty in predictions by performing multiple forward passes through the network with dropout enabled. Bayesian neural networks: a probabilistic approach to neural networks that explicitly accounts for uncertainty in the model parameters. Challenges and fixes. Challenge 1: overfitting: the model learns the training data too well and performs poorly on unseen data. Sample use case that resulted in challenge 1: training a neural network on a small data set with a complex architecture. Fixes to challenge 1. Regularization techniques: L1, L2 regularization or dropout to prevent overfitting. Data augmentation: creating more training data by applying transformations to the existing data. Early stopping: stopping the training process when the validation loss starts to increase. Challenge 2. Underfitting. The model does not learn the training data well and performs poorly on both training and unseen data. Sample use case that resulted in Challenge 2: training a neural network with a simple architecture on a complex dataset. Fixes to Challenge 2: increase model complexity, add more hidden layers or neurons, use more powerful activation functions, tune the learning rate to allow the model to learn more effectively, train for more epochs. Challenge 3: vanishing. Exploding gradients. Gradients during backpropagation become too small or too large, hindering the training process. Sample use case that resulted in Challenge 3: training a deep neural network with many layers. Fixes to Challenge 3: use appropriate activation functions. ReLU can help to prevent vanishing gradients. Gradient clipping, limiting the magnitude of gradients during backpropagation. Batch normalization, normalizing the activations of each layer, improving the stability of the training process. Challenge 4: local minima. The optimization algorithm might get stuck in a local minimum, preventing the model from finding the optimal solution. Sample use case that resulted in Challenge 4: using a gradient descent algorithm to optimize a model. Fixes to Challenge 4: use different optimization algorithms. Stochastic gradient descent (SGD) with momentum. ADAM. RMS prop. Initialize weights randomly. Train with different random seeds to explore different parts of the parameter space.